Well, one main challenge to Acorn's domination of the education market in Britain comes from research machines who had nothing more interesting than their RML 480Z with which to tempt the schools. Now here comes the new Nimbus, with the speed of an IBM AT, a minimum of 192K of RAM, and a starting price of under £1,000 for schools. There's a hard disk version for under £2,000. The interesting extra to protect software when the Nimbi are networked together is this dongle. It acts as an ignition key to activate programs which only a certain number of people have access. With real business applications, speed is more important. Files are going to be bigger and much more complex. Business machines now use 16 or even 32-bit processors with at least 500,000 characters of internal memory, so they can pull in more data at a time, usually from a 10 or 20 megabyte hard disk. The programs tend to be better written, probably in machine code for speed, and they can cost several £100s. Well, this is a 16-bit Nimbus machine which is going to look through the same 154 records and extract yellow flowers over 1 meter high, and it's really quite rapid. Here we go. Already we've got goat's beard, there it is, and 154 records, 6 records, so it's very, very fast. Just about time for a sip of Fred's tea. Well, this is still only the simplest form of database though, just the equivalent of a card file. Real business applications need more versatile systems. We'll be looking at the range of database packages available for business micros later in the series. What are the essential ingredients of an expert system?
Well, I think, Mac, the best way to explain that is to give you an example. We've used an expert system tool here to set up a simple expert system to really illustrate some of the points I want to make. It's a fairly simple system. It advises us on what type of safety fence we need on a road, a motorway or a small road, to prevent cars going off the road and whatever. So let's first of all simply set the system going and see what answers we get. Now you can see it's now asking me what is the speed limit at the point under consideration, and this will look like an exactly normal program at this time, and we'll answer 70 miles an hour. Now you'll find when it answers this that we can do something rather different with an expert system. It's asking us here, where should we put the fence? On the verge, central reserve, or unknown, or whatever. But we can do something different. We can actually ask, why? Why are you asking us this question? And when it does this, it comes back with a rule. And you can see the rule is saying if the speed limit is greater than or equal to 60, and the site being considered is the central reservation, the road type is rural, etc., the traffic level is very heavy, then in fact a safety fence is needed.
Because this acts almost as an audit trail to the expert to make sure it's absolutely correct. That why is a very important part of an expert system.
This is the key principle actually. The knowledge is stored in the program as it is written here. So that if in fact an accountant was looking at this, or a road designer, he would understand it. Whereas in a traditional program, if an accountant looked at it, he wouldn't understand the code.
So if, for example, the tax rates changed, the accountant, first of all, wouldn't know where to find the tax rate, and he wouldn't know how to change them if it was written, for example, in COBOL, but here he could actually check it out.
Exactly, and it's important, of course, because with experts, their expertise changes. You can't freeze an expert's knowledge.
This has been written in an expert system called XI. What's so special about this?
Well, it's an attempt to produce a slightly more generalised tool. So it's an empty expert system, and you can put knowledge in it and it'll solve your problem. It'll work in certain specialised situations.
It's called a shell. Is that a technical term?
That's right. A shell empty of knowledge.
Empty of knowledge. And who puts the knowledge in? Is it the expert himself or somebody who translates it from the expert?
Well, that depends on the situation. You'll see later how we might be able to do it directly, but often there's a knowledge acquisition stage, which is quite difficult, because experts often don't understand what their expertise actually is.
Thank you, Jim.
Here on the Nimbus, I've got another system. Remember, what we're trying to do is write things that'll help students and teachers understand what expert systems are.
Now, so you've got a set of rules here, and these really are in plain English, apart from the fact that they're sort of formally laid out.
Yes.
And it seems to be something about soufflés. Why have you chosen soufflés?
All right, we wanted a fault diagnosis system, and we had to choose something that people would understand.
Right.
And soufflés, when you're cooking a soufflé, that's something that often goes wrong.
Yeah.
So that seemed to be something we could do a fault diagnosis system about.
Let's see how this works.
All right, let's ask it
and
to go.
plenty of definable solutions as well as to why it's gone wrong.
Soufflé, cooked a soufflé,
it's
and it says that it's unappetizing. We might want to ask why. So I just press one button, and it comes up with a list of reasons why it might be unappetizing.
Plenty of ways, okay.
Okay,
Yeah.
and if I select one of them, for example, if you ever cooked a soufflé, you'll know that it often doesn't rise.
Yeah, never.
That's
never,
right.
In my experience,
then
let's
I can
find out
ask why, all right?
Yeah.
It'll say the temperature is too cool,
Yeah.
eggs are underbeaten, or the mixture is the wrong
So
consistency.
you get alternatives. Now, could you actually add a rule to that? I mean,
Yes, all right, let's have a go. The temperature is too cool if the oven is broken. Okay, there's a reason why it might be too cool.
Yeah.
And now if I ask why, it'll say
It's been
the oven's broken.
added to the information.
That's
now,
right.
using this system, your pupils, they get a chance to get their hands on the experience of being a knowledge engineer,
Yes.
an expert, and a user.
That's right. We're trying to teach people what expert systems are about. And to do that, we're sort of taking each of the ideas of expert systems and writing little programs about them.
And you think it's important that the man in the street gets used to this idea?
Well, if expert systems are going to be used in their jobs later on, or if they're going to use them when they come into contact with people like citizens' advice bureaus, they're going to need to know what an expert system is, and they're going to need to know how it works.
Right, Jonathan, thanks very much. A lot of applications nowadays are being written in a language called C. It's very fast and it's portable. And that means that you can run a C program easily on a range of machines. Here's a listing of a simple C program on the Nimbus to print a table of temperature conversions from Celsius to Fahrenheit. Now, this was all typed in on a word processor. To turn it into a program that the Nimbus can run, it has to be compiled. That means running another program that converts the text into Nimbus machine code. But this listing could be compiled to run on a number of machines, and that's what makes it portable.
This is Lotus 123, set up to look like that example. Now here we've got columns for the materials, the costs, the labour and the wages. And they've been itemised for the bricks, mortar, windows and glass. Here's the total cost, and here's the amount for the estimate, £1,393. Now notice that here we've only allowed for 2 windows, but just watch what happens, particularly to this final cost here, when I change the number of windows to 3. Enter 3, and they're all recalculated instantaneously, and the new cost is ready straight away. There it is, £1,489. Now that happens because there are rules which relate those numbers one to another. So for example, the cost of the windows in this box here is the number of windows times the cost of each. And the amount of glass you need, that's what we show here, also depends obviously on the number of windows. Now I put those rules in when I set up the spreadsheet, and you can see the rule for each box in this corner here. So box B9, that's B9, the amount of glass, is defined as box B8, it is B8, number of windows, times 2. So that's the number of windows, B8, times the amount of glass for each. Now we've taken each window as being 2 square metres. Right, let's move over to another one. C9. C9, the total cost of the glass, is B9, that's the amount of glass needed, times £12. That's the cost per square metre. And similarly, there are other rules for every box on the grid. Now, things can change. Supposing, for example, the rate for the glazier goes up from £50 a day, which I've allowed here, well, I simply change that rule. And the spreadsheet can get bigger. Supposing I want to be a bit more realistic and include the cost of plastering the walls. Well, that will need a new row, and a sensible place will be up here, just under those items for the walls, perhaps under the mortar. So I'll insert a row for the plaster. There we go. Insert row. Oh, by the way, this system uses a software add-on called Howl, which allows me to make all kinds of changes like this very simply. Insert row, enter that, and it does so straight away. That doesn't upset the system. The software is smart enough to adjust all those box numbers automatically. Right, there's a new row there, and I'll call it plaster. Enter that, and now I need a rule for how much plaster. Well, I'll just make one up. Suppose the number of cubic metres of plaster just happens to be the number of bricks divided by 8,000. It's got to depend on the area after all. So, right, number of bricks, that's what we've got in box B6. So I enter plus B6. The plus means a formula is on the way, divided by 8,000. There we are. I put in the formula, but watch what happens here. A number goes in. It's done the calculation immediately. And similarly, I can fill in all those other blanks. Now, this is a fairly small spreadsheet, but you could work with a spreadsheet which was hundreds of boxes in each direction, and then it would be absolutely indispensable. So to sum up, a spreadsheet is simply a series of rows and columns filled with numbers. Many of those numbers are related to each other by rules. So changing one number will automatically change all the other numbers that are related to it. To use the forbidden cliche, it's a very powerful piece of software.
Very expensive piece of software too, isn't it?
Yes, I'm afraid it is. The 123 is about £250, and if you want HAL, that's about another 130.
And you have to run it on a business computer with enough memory to cope with it.
Windows is very useful where repetitive but complex tasks are required to be used. With Windows, they can be used very, very easily. Mm-hmm. But the real fundamental use of Windows, which most computer manufacturers use, is to give a consistent interface to different programs running on the computer, and more importantly, to allow different programs to be run simultaneously in the memory of the computer.
That's quite difficult to understand in talking about it. Can we have a look at it?
It's much easier to show than to talk about, certainly. Well, here I have a typical word processor, and I have started to create a document in this word processor. I would like to insert a table of data, and this table of data will be created separately in a spreadsheet program. So let me open up my spreadsheet program. So here we are with Microsoft Multiplan with some data on butterflies. Let me show that we can add some more data. There we are, and the totals have been calculated. I now wish to take this table of data and copy it across to my word process document. Let me select the area which I want to copy across, issue the copy command, position my cursor where I would like the information to be inserted, and hey presto, we have it inserted.
Doing that in the operating system commands will be very, very hard, I suspect, or even it may be impossible.
Very hard, and in many cases certainly impossible, but I think here the simplicity and the speed with which it was undertaken is most impressive.
It certainly is.
There are many different ways of getting a micro to talk to you.
Some machines, like this RM Nimbus, can even talk in your voice.
This Nimbus works like a digital sound recorder. Earlier today I used a microphone to record that sentence, and the Nimbus stored away some 8,000 samples for each second of speech. To speak, it just reads those samples back. Well, that's all very well, but what can it do that a £20 cassette recorder can't? Well, of course, a computer can decide what to say and when under the control of a program. For instance, this is a machine you might find in schools. Just imagine the potential for software that can do this kind of thing in the teacher's own voice.
Well done, Katie. You've scored 9 out of 10.
Excellent quality, but 30 seconds of speech would use up about 128 kilobytes of memory. That's the equivalent of about 50 pages of typed A4, and it's far more memory than the average home or school micro can offer.